Hi, y'all. Today we're going to do our lecture on related rates. As always, I need to pull up those notes. This is one of my favorite units to teach because there's application in it. And so I think it's just a little more fun. But it can be a little overwhelming for some students. I'm going to try my best to make it as easy as possible. So related rates, they are rates that are related, obviously. Rates means you're taking the derivative with respect to time. So anytime you're thinking about a rate of something, you're thinking about that derivative, whatever that variable is, with respect to time. So this is an example of how you might find the derivative of a function with respect to time. So this is kind of like implicit differentiation. Remember, if you have y cubed, you would say 3y squared, and then you write dy dx. Well, if we're taking the derivative with respect to time, usually none of our variables are actually time. So you're going to have to write d whatever dt after every single variable. So the derivative of area is dA dt. The derivative of pi r squared, this is just the power rule. So you pull the two in front, pi r to the first power, but then it's like implicit differentiation. Now I'm going to write dr dt after it. So that's an example of how to take the derivative with respect to time. So let's jump into this first example. Assume x and y, find the indicated rates given the other information. So we have this function, it's a circle, x squared plus y squared equals 4. And then it says the rate at which y is changing with respect to time is 5. And then it says when x is 1.2 and y is negative 1.6, find dx dt. So we need to take the derivative of this function with respect to time so that these things show up in our equation. So the derivative of x squared would be 2x and then dx dt. Plus the derivative of y squared is going to be 2y and then dy dt. And then the derivative of 4 is 0 because it's a constant. At this point, I get to plug in the stuff that it told me. It says dy dt is 5, so that's going to go right here. X is 1.2 and y is negative 1.6. So we say 2 times 1.2 times dx dt plus 2 times negative 1.6 times dy dt, which is 5, equals 0. And so then what's this going to be? That's going to be 2.4. 2 times 5 is 10 times negative 1.6. So that would be negative 16 equals 0. So then we add the 16 over. So 2.4 dx dt equals 16. And then you divide by 2.4 to solve. So you would get that. That would be your answer. That's the rate at which x is changing with respect to time. Now, this is the steps to approach any problem, because what happens in this unit is you have different types of word problems and they seem like, oh, these are completely different situations, and they are, but the process in which you solve for each of these is very similar. The first step is to draw a sketch if possible. And when you draw your sketch, I'm going to add in here, things that change get a variable. That means they get a letter like X, Y, H, R. Things that stay constant can get a number. That is very important because if I draw a triangle, but then this is moving, I don't want to label it 5, even if it's 5 in an instant, I want to label it X. Okay, so you only get to label things that change with variables. Things that are constant can have a number. Then you write down all the given information, which I will explain to you how to do this as we're kind of combing through the problem. Look for things like how fast, look for words like changing. All these things indicate it's a rate with respect to time. Then you're going to write an equation. Now, step 3 is where it differs, right? You're going to have area equations. Sometimes you're going to have volume equations. Sometimes you're going to have triangle equations like Pythagorean theorem. So you're going to have different situations. We'll have a different equation. You write down that equation. And after you write down that equation, you're going to take the derivative with respect to time. And then you get to plug in the stuff you know and solve for what you don't. So let's get started kind of walking through these steps. The radius of a sphere is increasing at a rate of 2 inches per minute. So let's write that down in math speak. This is like when you were in elementary school and you learned all together means add, or difference means subtract. When I see increasing at a rate and I look at the units are a clue. This is something over something. Increasing at a rate, so the radius, what is increasing? It's dr dt is increasing at a rate of 2 inches per minute. Increasing means that this is positive, okay? Find the rate of change of the volume. So we're looking for dv dt, and I always put this bar, and that bar means when, okay? When the radius is 6. Now, don't touch any of that stuff until after you take the derivative. That's really important. Don't touch anything over here until after you take the derivative, because it's not always 6. Now we wrote down all our given. A sphere, we don't really have to draw a picture. I could, but it doesn't really help us in this situation. This radius is changing. I want to write down the equation. The equation of a volume of a sphere is 4/3 pi r cubed. At this point, we can take the derivative of everything with respect to time. So it's going to be dv dt, and this is just power rule. So pull the 3 down. These 3's will cancel. Pi r, subtract 1 from the power because it's power rule, and then write dr dt, because you're always going to write d whatever variable dt. dv dt is what we're trying to solve. Now, at this point, after I take the derivative, then you can plug in. You like Dr. Pepper? dp. Hopefully you remember that, dp, Dr. Pepper. Derivative, then plug in. Now I can plug in this stuff because it's after I took the derivative. So dv dt equals 4 pi, what's the radius? 6 at this instant. dr dt is 2. So that's 36 times 4. What is that? 144 times 2, so 288. 288 pi, and now volume over time. Volume is going to be measured in inches cubed because it's 3D per minute, because this dv dt, d is like delta. It's like a small delta, change in volume over change in time. So your unit should always check out. Let's do the next one. A point is moving on this graph, and then it says when the y coordinate is decreasing, so I see this change happening. So that would be dy dt. Decreasing means it's going to be negative 2 units per second. How fast means you're looking for something else. Dx dt equals what at this moment when we're at 3, 0. So we're going to write down our equation. This time we don't have to come up with an equation because they just gave us one. And we're going to take the derivative of this, because remember, you take the derivative, then you plug in. So what's the derivative of this? It is 8x dx dt plus 18y dy dt equals, don't forget the derivative of a constant is 0. Now I can plug in my stuff. 8 times x at this instant is 3. Dx dt is what we don't know, so we're solving for that. Plus 18y is 0, dy dt is -2. This just zeroes out then because that's 0. So I get 24 dx dt equals 0. And then to solve, I actually divide, so I actually get 0. And so it would be 0 units per second. All right. Let's move to the next one. A rowboat is being pulled towards a dock from a bow through a ring on the dock 6 feet above the boat. This time they drew a picture for us. If the rowboat is hauled in at a rate of 2 feet per second, how fast is the boat approaching the dock when 10 feet? So I don't like how they label this. I don't like that. I'm not doing that. Because it's not always 10 feet, right? It says it's being rowed in. This right here is actually changing. So we need to call it something. Usually I would call this distance x, and this distance y, and this distance r. You don't have to call it that, but it's a hypotenuse. A rowboat is being pulled towards the dock through a ring 6 feet above the boat. Now this could be 6 because this is always going to be 6. If the rowboat is hauled in at a rate of 2 feet per second, so what is changing at a rate of 2 feet per second is this string right here is being pulled in at a rate of 2 feet per second. So whatever you decide to label this, that's what you're going to write, dr dt or dh dt or whatever you're going to call this, dz dt equals 2 feet per second. How fast is the boat approaching the dock? So that would be this part, x. So what is dx dt? when the 10 feet of row. So that's when the R is 10. I don't like putting this as constant here because I'm going to write an equation looking at this triangle, and I don't want to write 10 in my equation because it's not always 10. So how do I relate the sides of a right triangle? That is Pythagorean theorem. And so anytime you have distance or anytime you have all the sides of a right triangle, I want you to think Pythagorean theorem, which is a squared plus b squared equals c squared. So I know x squared plus 6 squared equals r squared. Again, do not put 10 in here because it's not always 10. I can put 6 here because this is not changing here. So that can be constant. The derivative of this is 2x dx dt plus 0 equals 2r dr dt. So x right now is, we don't know x. So sometimes that happens. You have to do an extra step. So I like to make what's called at this instant box. Think about it as like a snapshot in time. At this instance, this is 6 and this is 10. So what is this side? You can do Pythagorean theorem to solve, or you can know that this is a 3, 4, 5 triangle. 3, 4, 5 triangle. This is just 3 times 2, and this is 5 times 2. So that means this is 4 times 2, which would be 8. So our missing side is 8. dx dt is what we're trying to solve for. 2 times r at this instance is 10, and dr dt is 2. Or I just need to put -2 because it's being pulled in. So r is decreasing. So I get 16 dx dt equals -40 divided by 16. Those are both divisible by 4, so that would be r divisible by 8. -5 over 2. Feet, is it feet per second? Feet per, yeah. Or -2.5. Because x is getting smaller, right? This distance is going to be getting smaller. So that's why this rate is negative, because this is getting smaller. Okay, so again, Pythagorean theorem. These guys are changing, so they get variables. This one is constant, so he can say 6 because he's not changing. So the derivative of him is 0 because he's not changing. Derivative is rate of change. So we took the derivative, we plugged in what we needed. When we are missing a side, we can use Pythagorean theorem or triples. Triples are like 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17. Just kind of, it's helpful to memorize those because then you don't have to solve Pythagorean theorem. But you always can just use Pythagorean theorem to find that missing side. Then you plug in what you know and solve for what you don't. Suppose that here's our cost, our revenue. Okay. Production is increasing at a rate of 600 calendar. Okay, hold on. Where the production output in 1 week is X calculators. Okay, so the production is, so I was saying dx dt. So dx dt is 600 calculators per week. When the production output is 2000, find the rate of increase or decrease. So we're trying to find dc dt and dr dt and dp dt when x equals 2000. Okay, so C is this 80,000 plus 30x. dc dt then would just be 30 dx dt. What is dx dt? 600. So we just get 30 times 600. So that would be 18 with 1, 2, 3 zeros. So $18,000 cost would be dollars per week. Okay, so it's increasing $18,000 per week. The production. Okay, then it says, now I'm going to find dr dt. Now r is this guy here. R is 300x minus x squared over 20. So dr dt would be 300 dx dt minus, bring the 2 down. So 2 over 20 x dx dt. 2 over 20 is 1 over 10. So now I'm going to plug in my stuff. So 300 dx dt is 600 minus x at this instant is 2000. We didn't have to use that in the last one because x went away over 10 because it's 1/10 x, and then dx dt is 600. Okay, so I got 3 times 6 again, so 18 with 1, 2, 3, 4. 1, 2, 3, 4 zeros minus this 10 will take away one of those zeros. 6 times 2 is 12, and I have 1, 2, 3, 4. 1, 2, 3, 4. So 120,000, 180,000. So that would be 60,000 is the difference. So that's the rate at which the revenue is increasing. I'm sorry. So that would be dollars per week. And then this, I don't have to rewrite the whole equation, because if I take the derivative with respect to time, it's just subtracting these rates from one another. So revenue minus cost change. So it'll be 60,000 minus 18,000. So $42,000 per week is the rate at which the profit is increasing. At that, when you're producing 2,000 calculators per week. And then lastly, a retail store estimates this is the sales. The current weekly advertising costs are $4,000, and these costs are increasing at a rate. The current, okay, so we got to look at what they're talking about. It says X is defined, this is advertising cost is X. Weekly advertising costs are $4,000. So X equals 4,000. And are increasing at a rate. Increasing at a rate, that means you're doing to something dt, and this was defined as X. So dx dt is $400 per. Now we're looking for the rate of change of cells. So we're looking for dx dt. So basically, we just have to take the derivative of this function they gave us. So dx dt, the derivative of this is just 0 minus 30,000 e to the negative 0.00025x. And if you remember, e is e to the u times the derivative of u. So then we're going to multiply by the derivative of that exponent, which is just going to be the coefficient in front of x. And then we want to evaluate this. Oops, and then dx dt. And then we want to evaluate it with these values. So it's going to be negative 30,000 e to the negative 0.00025 times x 4,000. And then times dx dt, which is 400. Let me see if I can grab my calculator really quickly. Plug that in for y'all. Negative 30,000 times e to the negative 0.12325 times 4123 times 400. Okay, so I got negative 4. Hold on. I didn't multiply times that. I didn't multiply times negative 0.000. We're going to multiply times that too. I didn't copy that part. Okay, so I get 1103.64 if I round to the nearest cent. And the units, it says, so it'd be dollars per week. Or dollars per cost. No, per week, because it's per time. Okay, so that is how you do that problem. As always, I'd like you to attempt your assignment and reach out to me if you have any questions.